Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy professor here at Foothill College, and it's a great pleasure for me to welcome everyone here in the Smithwick Auditorium and everyone listening to us around the world on the web to this program in the 15th annual Silicon Valley Astronomy Lectures. This is a program where we bring together public audiences with distinguished speakers from the world of astronomy telling us about the latest ideas and developments in our exploration of the universe. We're very grateful to our co-sponsors, NASA's Ames Research Center, the Foothill College Astronomy Program, the Astronomical Society of the Pacific, and the SETI, the Search for Extraterrestrial Intelligence Institute. All of them here in Silicon Valley, helping us to get wonderful crowds and wonderful speakers for this series. Tonight's program is a celebration of the International Year of Light, being celebrated by our physics colleagues around the world. Part of what we're celebrating is the 100th anniversary of the first introduction to the public of Einstein's general theory of relativity. So this is 100 years of relativity. That's part of this celebration of the International Year of Light. And our speaker is very much in that kind of celebratory mood. Dr. Bennett is the author of college-level textbooks in astronomy, astrobiology, mathematics, and statistics, as well as the popular books, What is Relativity, which is the subject he's discussing tonight, and Beyond UFOs, The Search for Extraterrestrial Life. His 5 books for children are currently aboard the International Space Station, and they're being read to kids on Earth by the astronauts during the regularly scheduled story time from space. Dr. Bennett has a PhD from the University of Colorado, has been a visiting senior scientist at NASA headquarters, where, by the way, he started much of the current effort that NASA has in education and outreach. He is a wonderful speaker and a dedicated teacher, so it's for me both a personal pleasure and a professional privilege. Talking about 100 years of Einstein's relativity and how it underlies our modern understanding of the universe, it's a pleasure to present to you Dr. Jeff Bennett.
Thank you very much. It's a great pleasure to see so many of you here. I really appreciate it. I've been doing this talk in a number of places I'll show you in a few minutes, and we had a pretty big crowd at the one I did in my hometown of Boulder, Colorado, and one of my friends reminded me that it was the first time I'd ever had a sellout crowd and that I shouldn't assume they came for me. You all came for Albert. So I want to thank Andy for inviting me here. I really appreciate that, and everyone who sponsors the talks, and Foothill College, thank you for bringing me out. What we're going to do tonight is I'm going to talk about this topic, what is relativity? I am going to assume that you have no idea what the answer is, and therefore that we're starting from a ground level. So I'm going to talk and try to make sense of that question to you. It's an interesting question in science because it's a rare topic where virtually everyone has heard of the theory of relativity. Virtually everyone knows that Einstein is famous, and yet very few people know anything about relativity or why it made Einstein so famous. So my goal tonight is simply to answer that question, what is relativity, for you? And you can see the subtitle that I have on the talk in the book, An Intuitive Introduction to Einstein's Ideas and Why They Matter. I want to also talk to you in particular about why I think relativity is not just important scientifically, but important to all of us. Why I think everyone should learn something about relativity. Why, in fact, I believe it should be part of the K-12 curriculum starting in mid-elementary school. So I will try to convince you of those things tonight as well. Before we get into any of the details, I'll just give you the short answer to the question, what is relativity? The short answer to the question is, relativity is our theory, our modern theory that gives us our current understanding of space, time, and gravity. Now I want you to think about that for a moment. Space, time, and gravity. That's pretty much everything. So relativity is a key part of everything in modern science. Now I'll try to give you a little bit deeper insight into that in the rest of the talk. But first I want to point out, as Andy already did, the timing of this talk is not an accident. This is the 100th anniversary of Einstein's publication of general relativity. In 1915 is when he published the general theory. And the United Nations did designate this in honor of that as the International Year of Light. And back just a few months ago, November I think it was, I saw a little posting from the groups that were organizing this International Year of Light saying they wanted to have people go out and tell people about relativity, teach about relativity, do outreach programs and so on. I thought, well, what can I do? Well, I had this book on relativity and I thought, well, I can go talk to people. So I decided that for my personal contribution to the International Year of Light, I would just talk to anyone who would listen to me. I appreciate you being among those people who are willing to listen, at least so far. And so I put together this relativity tour. It was not very well organized. Basically, I just emailed people that I knew and said, do you want to have me come talk? And if they said yes, then I came. And so you could see some of the places I've been. And incidentally, for our web viewers out there, if you're watching this and you'd like to have me come talk wherever you happen to be, just get in touch with me, jeff@bigkidscience.com, and we can try to get me out to wherever you are. In addition to it being the 100th anniversary of relativity, this topic got on a lot of people's minds recently because of this movie. How many people have seen this movie, Interstellar? Oh, good. A lot of people in this audience have seen Interstellar. That's excellent. Hopefully you realized, maybe you did, maybe you didn't, that the movie Interstellar is actually very much about the theory of relativity. The executive producer of the movie was is a Caltech physicist named Kip Thorne, who's one of the world's leading experts in relativity. So he worked very hard to make sure that at least those parts of the movie that deal with relativity were scientifically accurate. If you're wondering which parts are scientifically accurate, which parts maybe not so much, I did a blog post on interstellar science, which you might want to check out. Now we'll go right into this issue of what is relativity, and the way I like to start out with this issue is by asking you a question. Most people don't know very much about relativity, but one thing you have heard of is black holes, and black holes are actually a part of the theory of relativity. So here's your question. Imagine that the sun magically collapsed into a black hole retaining the same mass. What would happen to the Earth? And you can see some multiple choice options on the screen, but you don't have to read them, and you don't have to commit to an answer right now. I just want you to think about, maybe if you do know the answer, you don't, what would happen if you asked other people this question? What would happen to the Earth if the sun collapsed into a black hole without changing its mass? Some of the best people to ask this question to are kindergartners, because they'll give you the same answer that most adults will, which is that the Earth would be sucked into the black hole. So choice A is by far the most popular answer to this question. And so the way I want to start out is by thinking about whether or not that is the correct answer to the question. So how are we going to do that? Well, you remember I told you that relativity is a theory of gravity. Some of you know that relativity was not our first theory of gravity. There was a theory of gravity before Einstein came up with general relativity. The theory of gravity before that was Newton's theory of gravity. And in fact, Newton's theory of gravity works really, really well. You might even wonder, why did we need a different theory of gravity? Newton's theory of gravity works so well. It explains why things fall to the ground when you drop them. It explains Earth's orbit around the sun. You can use Newton's theory of gravity without anything else, without Einstein's theory, to take a spacecraft and navigate it among the planets, to fly past Pluto, to land on a comet like we did last fall. Newton's theory of gravity works really, really well. The only time when you need Einstein's theory of gravity instead is when the gravity becomes extremely strong. There, Newton's theory begins to break down a little bit, or if you measure with extreme precision. But in general, Newton's theory of gravity works great. There are only certain circumstances in which you need to go broader into Einstein's theory. And Out here where Earth orbits the sun is one of those places where Newton's theory of gravity works really well, and therefore to answer this question we don't even have to think about relativity. We can just use Newton's theory. Newton's theory of gravity tells us what happens to objects under the influence of gravity. It tells us that they orbit. We usually think of orbits as being bound, elliptical orbits that go round and round and round, but Newton's theory of gravity tells us that's not the only possible orbit. You can also have orbits that come in from far away and go out and don't come back again, and those technically can be in the shapes that we call parabolas or hyperbolas. So basically, Newton's theory of gravity tells us that your allowed orbits under gravity are ellipses, parabolas, and hyperbolas. And the important thing to notice about this list is that it does not include sucking. And therefore, we get our first major idea that I want you to remember from tonight, which is that black holes don't suck. They're actually really cool, in fact. And I'd love to take you on an imaginary journey to a black hole, but if you get to read my book, you'll see a journey to a black hole in the beginning. But for tonight, I want to focus on the question of what is relativity. We won't have time to go through that. So we'll just stick with keeping this idea in mind. Incidentally, the movie Interstellar, for those of you who've seen it, and for those of you who've not, I'm not going to do any major spoilers here. It won't ruin it for you, don't worry. They actually do a very nice job of this. In that movie, they go through the wormhole and come out around this supermassive black hole in another galaxy. And what do they find when they get there? They find planets. And what are the planets doing? They're orbiting the black hole. They are not getting sucked into it, which is correct. They do it right. Same thing with the spaceship. The spaceship orbits the black hole. It does not get sucked in. They did that correct. And in fact, the only place where they make a very minor error with this regard to this particular topic in the movie is when Matthew McConaughey's character, Cooper, I believe it is, takes his spaceship and goes diving into the black hole. One of the other crew people says something about, oh, he got sucked into the black hole. Well, he didn't get sucked into the black hole. He dove into the black hole. I just want you to think about this. If you're, say, in a kayak and you're paddling down the river and you go, oh, there's a waterfall ahead of me, and then you paddle harder toward the waterfall, and then you go over the waterfall, don't say it happened because the pool at the bottom sucked you in. It was your own fault. Okay? And in the same way, if you dive into the black hole, yes, you're going down. Don't blame it on the black hole. What is relativity? Well, we speak about the theory of relativity, but one of the things that sometimes throws people off is that the theory, sometimes we say special relativity, sometimes we say general relativity. Why do we do that? Because Einstein actually published the theory of relativity in two distinct parts. The first part, the special theory of relativity, published in 1905, and then the second part, the general theory of relativity, in 1915. A lot of people hear this and they say, gosh, why did Einstein think his theory was so special when he hadn't even finished it yet? And the answer is he didn't mean it that way. He's using physics terminology. He's using special to mean a special case. And the special case for special relativity is that we ignore gravity. So special relativity does not deal with the effects of gravity at all. Why did he do it that way? Why did he first publish a theory without gravity and then add gravity later? Well, there's a few reasons for it. One reason is that it's easier to do it that way mathematically, and don't worry, we're not going to do any mathematics tonight. There's no mathematics in my book. But if you do study relativity and you need to do the mathematics of it, you can actually do most of special relativity with nothing more than about 8th grade algebra. For general relativity, you need far more advanced mathematics. So it's easier to do that one, special relativity, first. Another reason, though, the more important reason, is what he was trying to do. And here's where you have to understand Einstein a little bit. Einstein got into this because he said that when he was a teenager, he used to try to imagine what would it be like to ride on a beam of light. And when he thought about that question, what would it be like to ride on a beam of light, he encountered all these strange paradoxes, things that didn't seem to make sense about the world. And he wanted to figure out what would make the world make sense. And special relativity, he was really going after those paradoxes, trying to understand how he could make sense of what it would be like to ride on a beam of light. But in the meantime, between those teenage years and when he published the theory of special relativity when he was 26 years old, he learned physics. And in learning physics, he realized that there were some significant problems known at the time with physics. I'm not going to go into any detail about them, but for those of you who've had some physics background, in brief, the problems had to do with the laws of electricity and magnetism. And those were problems that a lot of people were working on trying to solve. And in fact, when Einstein published that paper in 1905, the title of it was On the Electrodynamics of Moving Bodies. So you can see his 1905 paper solved these well-known problems in physics that people had been working on. In fact, other people were working on them. Other people were close to the answers. Most historians of science will tell you that if Einstein had not published his theory of special relativity when he did in June of 1905, someone else would have done it probably that very same year. People were that close to the idea because there were these known problems that needed to be solved. Well, he solved them. For most other physicists, the problems were solved. We were done with that. But remember, Einstein was coming about it from that what would it be like to ride on a beam of light framework. And he realized that even though he had resolved most of the paradoxes that he had encountered when he thought about that question, he hadn't quite resolved all of them. There was more that needed to be done. And therefore, he kept going and ended up with the general theory of relativity. And here, most historians of science will tell you he really leapt out ahead of other people because he was thinking of it in this different way. And that if he had not published general relativity in 1915, it might well have been a couple more decades before anyone else would have landed on the same thing. So he really did think about things in an interesting way that I think is very valuable for all of us. Now, the theory of relativity has three words: theory, of, and relativity. Most people know what the word of means, but the other two words give people a lot of trouble, so I want to briefly spend some time on those two. First, what do we mean by theory? In everyday life, theory tends to mean kind of a guess. But that's not what we mean by theory in science. Now, admittedly, even scientists use this word incorrectly a lot. But when we're using it correctly, a theory in science is something that explains a wide variety of observed facts in terms of a few simple underlying principles and makes predictions that have been confirmed over and over and over and over again. So a theory is not a guess. A theory is something that we know. It's very solid. In fact, when you're using the term correctly, as we are with the theory of relativity, we're talking about something that is so well established that there's really no possible way that it could ever turn out later to be wrong. It could turn out to be incomplete or not the whole story, but it can't be wrong because it's been tested so thoroughly. And the great example of this, again, is Newton's theory and Einstein's theory. Newton's theory of gravity was not wrong. It gives you the correct answers that allow you to fly your spacecraft to other worlds. It works really, really well in many, many cases. There are a few cases where it begins to break down. So Einstein's theory gives you the correct answers in those cases, but Newton never claimed to have the answers for those. He gave the answers for the things he knew about at the time. His theory was correct as far as it goes. Einstein's theory is a broader theory of gravity. It shows us that Newton's theory wasn't the whole story. But Newton's wasn't wrong, it just wasn't the whole story. And in the same way, it's very likely that someday we will have a broader theory of gravity than Einstein's theory. That won't mean Einstein's theory was wrong. It gives us lots of correct answers. It'll just mean we'll have an even broader theory in the future. That's what we mean by the word theory. Now let's go to the word relativity. What do we mean by relativity? Well, the common myth is that Einstein said everything is relative. Einstein did not say that. Einstein uses the word relativity here because he's talking about one particular thing. He is talking about the relativity of motion. Now, from the relativity of motion, we end up with some relativity for time and space that we'll talk about, but the word relativity is meant for the relativity of motion. Now, this idea can seem a little bit strange, and there's a lot of ways of going about it. Like sometimes if it weren't for the videographer wanting me to stay kind of in one place, I'd walk across the stage, and you'd see me walking across the stage, and I'd tell you that, no, you're misinformed here. I'm just staying still while the stage moves by underneath me. But that sounds a little strange to a lot of people. So to try to get a better handle on what we mean by relativity of motion, I want you to think of a different example. Imagine that you're a world traveler and you get into an airplane in Nairobi, Kenya. And your airplane takes off and it flies across the world to Quito, Ecuador. And you fly at a speed of 1,670 kilometers per hour, and then somebody says, "How fast were you flying?" And you say, "Well, gosh, I just told you, 1,670 kilometers per hour. But wait. I didn't choose that speed by accident. I chose that speed because it happens to be Earth's equatorial rotation speed. So you see, the airplane flies from Nairobi to Quito at 1,670 kilometers per hour, but while it's doing that, Earth is rotating in the opposite direction at exactly the same speed. So picture, just like it kind of looks like as you're sitting out in the audience looking at the screen, imagine that you were watching this trip from the moon. What would you see happen? Well, you would see the plane lift off the ground right here in Nairobi, and it wouldn't go anywhere. It would just wait as the Earth rotated underneath it, and when Quito arrived, the plane would drop down. So from your point of view on the moon, the speed of the plane is 0. It goes nowhere while Earth rotates underneath it. So which answer is correct? Does the plane fly 1,670 kilometers per hour from Nairobi to Quito, or does it go nowhere while Quito comes to it? The idea of relativity, what Einstein means by relativity of motion, is that both are equally correct, but neither one has any meaning unless you specify what the motion is relative to. You can't just say, I was going 100 miles per hour. 100 miles per hour relative to what is important. You have to specify it. If you're running and you say, hey, I was running at 10 kilometers per hour, and you say, well, how far did you go in an hour? Nowhere. That would be true if you were running on a treadmill, right? Okay? So you can see how this idea works. Relativity is speaking of the relativity of motion. But in fact, while that is an important aspect of the theory of relativity, the real heart of the theory of relativity lies not in the fact that motion is relative. That's not really that surprising to people in general. It's that Einstein said there's two things in the universe that are not relative, that they are absolute. In fact, I think there'd probably be a lot less public confusion if instead of calling it the theory of relativity, he had called it the theory of the two absolutes. That probably would have been a good way to do it. And what are the two absolutes? Well, the first one is that the laws of nature are the same for everyone. In other words, whether you're here on Earth, on the moon, in an airplane, if you do the experiments, take into account any turbulence or other things going on, you'll always find the same laws of nature as anyone else would. That was not a surprise when Einstein asserted it. In fact, it had been generally assumed to be true since the time of Galileo, and the minor caveat, the reason he had to say it explicitly instead of just assuming everybody thought it was correct, is because I mentioned those problems with electricity and magnetism that he was trying to solve. Again, for those of you who have some physics background, one of the problems was that the laws of electricity and magnetism, Maxwell's equations, when you transform them to a moving reference frame, seemed to be changing, as though the laws weren't the same for everyone, depending on motion. So he was trying to restore that. But aside from that little caveat, the idea that the laws of nature are the same for everyone is generally not a surprise. We expect that. It's the second absolute of relativity that is a big surprise. And the second absolute is that the speed of light is the same for everyone. Now, why is this a surprise? Well, imagine that I'm in an airplane and I'm flying by you at 500 miles per hour, and I have a ball in my hand, and I throw it to someone a few rows up at a speed of 10 miles per hour. What will you see the ball doing from the ground? Well, before I even throw it, you see the ball going 500 miles an hour with me in the plane. Then I throw it at 10 miles an hour forward, so you're now going to see it going 510 miles per hour. That's simple. It makes sense. It's what we expect. But Einstein said, if you're doing it with light, it's different. With light, if I have a flashlight and I shine it on a person a few rows up in the airplane, I'll say the beam of light is going the speed of light, 300,000 kilometers per second. Using the same reasoning we just used, you would expect to say it's going the speed of light plus the 500 miles per hour of the airplane. But you don't. You see it going the same exact speed of light that I see despite my motion relative to you. That's weird. It's not what we expect. In fact, it's so weird that you might wonder, why would Einstein even say something like that? And there's two answers to why he would say something like that. The first answer is because, remember, he's thinking about what would it be like to ride on a beam of light and encountering all these strange paradoxes. And he realized at one point that he could resolve those paradoxes if the speed of light was always the same for everyone. It made sense to him that that had to be true. But in science, just because something makes sense is not good enough. You have to actually establish it experimentally, and the fact that the speed of light really is the same for everyone is an experimentally verified fact. In fact, the first experimental verification of this was done a couple decades before Einstein published his theory of special relativity. It's the famous Michelson-Morley experiment. The only problem was Michelson and Morley didn't quite realize what their experiment was actually showing them. They thought it was giving this weird result that they tried to, hedge why it would be doing that. Einstein basically said, well, why don't you just assume the result is telling you what's actually happening? So the speed of light is constant. It is the same for everyone. It's been measured, and if you don't accept just right off the experimental evidence, you can actually get this idea in a much simpler way. Every time you look through a telescope or look at photos taken from the Hubble Space Telescope, for example, the light from all those different stars and galaxies in the photos is coming from different things that are moving at different speeds relative to us. Some of the galaxies in Hubble Space Telescope photos are moving away from us at speeds very close to the speed of light. And yet, the light coming into our telescopes is always still coming at the same speed of light, no matter how those objects are moving relative to us. The fact that the speed of light is always the same for everyone, no matter how you're moving, how the object's moving relative to you, is simply an experimentally verified fact. And it is from this single fact that all the strange ideas of relativity flow. You can do what Einstein did, thought experiments, where you think about, okay, if this is true, then what's the consequences of that with various things with motion, and you will come up from that with all the major consequences that you've probably heard about with relativity: time changing, space changing, equals mc squared, and so on. If you get a chance to read my book, I have the thought experiments that will lead you to every single one of those conclusions. But because of our limited time tonight, I'm going to do just one thought experiment for you to show you only one of the consequences of relativity. And of course, I've chosen the one that is everyone's least favorite consequence of relativity, which maybe you've seen on t-shirts like this: 300,000 kilometers per second. It's not just a good idea, it's the law. You cannot go faster than light. You cannot reach the speed of light, and you cannot exceed it. And why is this everyone's least favorite consequence of relativity? Because we don't like being told what we can and cannot do. And this tells you, you cannot. So let's for a moment pretend that we can. How can we pretend that? Well, let's just imagine that I could build a spaceship, or you could build a spaceship that's not limited. We can go any speed you want. The only thing is, we still have to obey the two absolutes, right? The laws of nature are the same for everyone. That one's easy. And the speed of light is the same for everyone. So imagine I've built a spaceship. We're not going to limit the speed. We're going to let me go as fast as I want. Okay, and I want to go fast. I get in my spaceship. I go fast. Put it in second gear. I go faster. And I go and go. So I'm going so fast, you can't even imagine how fast I'm going. Okay? Now, that's really fast, and Earth is kind of small, so I better not be on Earth, because I would have crashed into something a long time ago. I got to be out in space. So I'm flying out through space in this really fast spaceship. That's great, but space is dark, and I don't want to hit anything. So I better have some headlights so I can see where I'm going, right? So I've got my headlights shining out in front of me so I can see where I'm going. This is really helpful, because we know I can see my headlights. How fast do I say my headlights are going? The speed of light, right? Everybody always says the speed of light. I say my headlights are going out in front of me at the speed of light. That's good. But for you, I'm going super fast. How fast am I going? Well, you don't know. You don't know how fast I'm going. But there are two things that you know. Number one, you know that my headlights are shining out there. How fast are my headlight beams going according to you? Speed of light. And you also know that they're shining out in front of me, which means that they're beating me, which means that I'm going less than the speed of light. See that? We didn't set any limits to begin with, but because everyone sees the same speed of light, there's no way I could ever be going faster than it. Because no matter what I do, you will always see my headlight beams going the speed of light and beating me. This is ironclad logic. I have had students come back to me 20 years after my class and say, I finally figured out a way around that logic. And they sit down and start explaining it to me, and about halfway through they go, and this is true, it's happened numerous times. About halfway through they go, oh, wait a minute, that doesn't work, does it? This is so solid that not even science fiction writers try to violate this rule. Instead, they look for loopholes. They jump into hyperspace. They travel through wormholes. They invent warp drive. But no one ever tries to move through space faster than the speed of light. Why? Because you can't. And in the same way, we could do other simple thought experiments about at the same level to derive all the other consequences. I won't go through them, but I want to just talk about a couple of them. For example, this famous one. Imagine that you took a trip from Earth to a distant star 25 light years away, and you could travel at 99% the speed of light the whole way. Don't actually try this. If you accelerate from 0 to 99% of the speed of light pretty much instantly, you will be squashed, so it's not safe. But if you could do it, you can figure out what would happen. Well, it's 25 light years in each direction. You're going a little bit slower than the speed of light, 99% the speed of light. Therefore, according to people on Earth, it will take you a little bit more than 25 years in each direction, so you'll be gone for 50½ years. So if you leave this year, 2015, you'll be back in the year 2065. But what will you see as the traveler on this spaceship? Well, you get into your spaceship and you start instantly going up to 99% the speed of light and somehow survive that acceleration. What are you going to notice? Well, strangely enough, you'll notice that if you measure the distance to the star now, all of a sudden it's not 25 light years anymore. Instead, it's only 3½ light years. And therefore, since you're going almost the speed of light, it only takes you about 3½ years to get there, same back, and you'll be gone for a total of 7 years. So you will leave. You will need 7 years worth of meals. You'll need 7 years worth of supplies. You'll have 7 years worth of heartbeats. In other words, if you're 40 years old today, you'll be 47 when you get back. But it will be the year 2065. 50 years will have passed on Earth. This is not science fiction. This is reality. This is what would really happen if you could do this trip. In other words, what we find is that space, the distance is measured differently depending on how you're moving. The time is measured differently depending on how you're moving. Space and time are not the same for different observers depending on how they're moving. They've become intertwined as what we call space-time. And one of the amazing things that Einstein showed was that even though different people will observe space differently and time differently, space-time, the four-dimensional combination of the 3 dimensions of space plus the 1 dimension of time, is the same for everyone. He shows that what is actually happening is when you're moving at a high speed, different observers relative to you will see more or less of the space, more or less of the time, but the total space-time will be the same for everyone. It's kind of like, in an analogy, if you go from point A to point B, well, in one coordinate system, you might say, well, x is this way and y is that way. So you'd say it's this far in x and that far in y. But in another coordinate system, you might say, oh, it's all along the y-axis because the x-axis is this way. But either way, the 2 points are the same distance apart. And Einstein said the same thing with space-time. 2 events, things that happen in a certain place, they're the same space-time distance apart, but different observers will measure the space part differently and the time part differently. It's kind of a strange idea to get your head around, but you can get your head around it if you think about it for a little while. Before I tell you how you're going to get your head around it, I want to convince you that you should by explaining why we know it's true. It's not because Einstein said so. It's because we've tested it. Now, we have not ever built things that travel. We cannot travel at speeds that go close to the speed of light, but we can build things that make subatomic particles travel close to the speed of light, like the Large Hadron Collider. In those accelerators, we can test these ideas that Einstein had predicted. For example, let's go back to the idea that you cannot go faster than the speed of light. Decades ago, we had particle accelerators that could make particles go at 99.9% the speed of light. Now we have particle accelerators that are thousands of times more powerful. And what do we get for that? A couple more nines in the 99.9. Why? Because no matter how much more energy you put in, you can never get all the way to the speed of light because you can't do it. It's not possible. There are certain particles that decay in characteristic amounts of time. Those particles, when you make them in a particle accelerator, last longer than they do when they're at rest. Why? Because time is running slower for them, exactly as Einstein said it would, just like our little example with the traveler to another star. In fact, the equations of special relativity allow you to calculate exactly how much slower time should be running, and the particles have been tested, and it's been confirmed to like 15 decimal places. Einstein's theory gives you the exact right answers. You can also measure it even at low speeds if you do precise enough measurements. E equals mc squared. Everybody's heard of that equation. Energy equals mass times the speed of light squared. What a lot of people don't realize is that equation is part of the theory of relativity. It's part of special relativity. If the rest of relativity is true, then that's true, and vice versa. And how do you know that this is correct? Because it explains how the sun shines, nuclear power, nuclear bombs. So every time you go out on a sunny day, you're looking at experimental evidence or direct personal evidence that relativity is correct. Remember I told you that relativity actually was solving these problems in electricity and magnetism. So the laws of electricity and magnetism turn out also to have relativity built into them. So every time you use a radio or a cell phone or a computer, you're getting further evidence that relativity is correct. So why is it that people have so much difficulty accepting something that has been so well tested? And the answer is because it seems weird, right? The idea that different people will measure the space differently and the time differently. It sounds very weird. And a lot of you are probably thinking that it's hard to accept because it violates your common sense. But I have good news for you. It does not violate your common sense. I also have bad news for you, which is that the reason it does not violate common sense is because when it comes to these kinds of ideas about what happens at very, very high speeds with relativity, you don't have any common sense. And that's not really meant to be an insult, it's just a fact. And it's a fact because by definition, common sense is sense that you have developed through things that you have commonly experienced. And guess what? You've never traveled close to the speed of light. The fastest spaceship humans have ever built is that New Horizons ship that will fly past Pluto this July. It's going 50,000 kilometers per hour. If you're a Superman fan, that's 100 times faster than a speeding bullet. And it's 1/20,000th of the speed of light. We don't have things that go anywhere close to the speed of light. You've never commonly experienced those kinds of speeds. So of course you have no common sense for it. The problem is you have common sense for low speeds, and you want to think that your low speed common sense ought to also apply to high speeds. But there's no reason why you should think that. And in fact, it doesn't work that way. All you have to do if you want to get your mind around these ideas of relativity is just keep thinking about them, working with them, until you build a new common sense that is the right one for high-speed situations. And if that sounds hard, I want to point out to you that you've done this kind of thing before, not with relativity, but now we come to audience participation, where I see if you're still all awake. Everybody point up. Oh, very good, and we have agreement on which direction it is. Everybody point down. Great, that is common sense about up and down. This is really good common sense about up and down. It explains why I should not jump off the stage. It explains why you should not jump out of buildings. You can use this common sense about up and down to play basketball. But some of you may not remember this too well, but if you think way back to this common sense which you developed at a very young age, it once caused a crisis for you. The crisis probably occurred somewhere in first and second grade. And the crisis occurred when your teacher showed you a globe. And you applied your common sense to the globe, up, down, and you said, oh my gosh, those poor people in Australia are in a lot of trouble. What was the problem? The problem was that your common sense, which is great common sense for a room like this, is not good common sense for the whole planet. It doesn't apply to the whole planet. For the whole planet, you need a different common sense. Up is away from the center, down is toward the center. And guess what? You got used to that idea. By now, it's probably so obvious to you that you don't even realize you're using a different common sense here in the room than you use when you think about the whole planet. With relativity, it's the same idea. You just have to use a different common sense for high-speed motion than you use for low-speed motion. But you've done it before, and if you make a little bit of effort, I'm confident that you can do it again. But that's all I have time to talk about with special relativity. Again, I hope you'll spend more time on it later or reading the book or so on. Now I want to move on to general relativity. Now remember, Einstein was adding in gravity with general relativity. Other scientists didn't really think there was much left to do, and that's why no one else was working on the same thing at the time. Why didn't they think there was much left to do? Well, because Newton's theory of gravity works so well. It had actually been used in the 1800s. Astronomers had noticed some little problems with the orbit of Uranus, which had been discovered in the 1700s, and this famous French astronomer, Urbain Le Verrier, in the 1840s did this calculation. He goes, you know what, we could explain the orbit of Uranus if there was another planet beyond Uranus that we don't know about yet, and it was right there. And so he wrote a letter to his friend who was at the Berlin Observatory. He said, why don't you point your telescope right there? So the guy did, and guess what he saw? Neptune. So the existence of Neptune was predicted using Newton's theory of gravity. It works great. There was actually one small other thing that was a problem with a known problem at the time Einstein got to work on this, and that had to do with the orbit of Mercury. I won't go into any details on it. Most other scientists didn't seem to be concerned enough about it to think there was a major problem, but it was important for Einstein because when he did come up with his general theory of relativity, the first thing he did was test it on the orbit of Mercury, and he resolved that problem, and that was when he knew he was on to something that was real, not just something that made sense, but something real because it gave him the correct right answer for the orbit of Mercury. But aside from that, there didn't seem to be anything wrong with Newton's theory of gravity. And the one thing that maybe you could have said about Newton's theory of gravity was it didn't make a lot of sense. Now, what do I mean by that? You have, let's say, the sun here, and Earth is orbiting the sun because of gravity. And that sounds all fine, but think about this for a moment. The Earth and the sun, they're 150 million kilometers apart. They don't have any eyes or ears or noses or sense of touch or anything else, or even brains. How do they even know each other are there? How is it that gravity can act between these two things that have no senses, no brains, at such a great distance? If you think about it, well, rather than me talking about it, I'll read this famous quotation here for you, because it explains the problem that we're talking about. That one body may act upon another at a distance through a vacuum, and force may be conveyed from one to another, like between the Earth and the sun, is to me so great an absurdity that I believe no man who has a competent faculty in thinking can ever fall into it. In other words, Newton's theory of gravity may work great, but it makes no sense at all. It's completely absurd. And some of you may be thinking, okay, Einstein, fine, you came up with a new theory of gravity, but do you have to be so rude to Newton? But Einstein didn't say this. Newton did. These are Newton's words about his own theory of gravity. Newton himself recognized that even though his theory worked really, really well, it just didn't seem to make much sense. And so Einstein was removing this absurdity with his general theory of relativity. Now, he was actually going about it, going back to his for different reasons, going back to his teenage, what would it be like to ride on a light beam? He came up with a very important idea that I'm not going to talk about tonight, called the equivalence principle, that he used to get at, in the same way that the speed of light being constant is the key to special relativity, the equivalence principle is the key to general relativity. But instead of going about it that way, I want tonight just to give you another thought experiment that gives you kind of the essence of what Einstein told us about gravity with general relativity. So for this, we need to do another little thought experiment. So this experiment is, imagine that you live a long, long time ago when you believe that the Earth is flat. And you're a wealthy patron of the sciences, so you decide to hire some explorers to explore your flat Earth. So you get two explorers and you say, hey, you go that way, and you go that way. Stay in a straight line and don't come back until you discover something really amazing. So off your explorers go in their straight lines in opposite directions, and sometime later they both come back and you go, oh great, what'd you discover? And they say, well, we ran into each other. If you truly believe that the Earth was flat, this would be a shocking outcome, right? How could that happen? But of course, we're not shocked at all, because we know the Earth is not flat. It's round, it's curved. It curves around in both directions, so if you go off in opposite directions, of course, you're going to meet on the other side. We expect the travelers meet because Earth is curved. Now let's do the same experiment, but let's do it in a more modern setting. So you're out in space, and you're floating weightlessly in your spaceship. And you send one probe off in that direction in a straight line, and the other probe off in that direction in a straight line. Would you be surprised if sometime later the two probes ran into each other? I can see you all thinking about this. The answer is maybe you think you'd be surprised, but really you shouldn't be surprised. We don't do this all the time, but we could, because, for instance, what's an example of floating weightlessly in space? Well, being in the space station. And if you're in the space station floating weightlessly in space and you send off one probe that way and the other probe that way, well, they're going to obviously meet up on the other side of the Earth. Okay? Natural. Why? Well, according to the standard explanation, because of this magical, absurd force of gravity that acts on them all without anybody understanding why. Now, Einstein didn't do exactly this particular thing, but you can kind of imagine using the way Einstein would have thought about these things, the way he did think about these things. What would Einstein say about this situation? He would say, well, you know, gosh, this picture sure looks a lot like the one you showed me a minute ago where they had the two explorers on the Earth. And you said the two explorers met because Earth is curved. Why don't you just say the two spaceships meet because space is curved? Wouldn't that be easier than blaming it on a magical force of gravity? And in essence, that is exactly what Einstein said. He said that gravity is curvature of space-time. You cannot visualize this curvature of space-time. You cannot even visualize curvature of space, three-dimensional space. Why? Because we live in the three dimensions. We can't picture the three dimensions being curved. We certainly can't picture the four dimensions of space-time being curved. But we can use analogies. Like here we see a two-dimensional analogy to it. So in this two-dimensional analogy, you see this curved sheet, and the idea is that space-time is curved by the Earth's gravity, so that if you're in the space station right here, you send one probe that way, the other probe that way, they're obviously going to meet on the other side. Why? Because that's the shape of the universe that they're in that location. There's no magical force anymore. The objects are just following the natural path allowed to them by the shape of space-time. It's just kind of an interesting way of thinking about it. It's a strange new idea, but this is what general relativity tells us. Gravity is curvature of space-time. Sounds good. Einstein did some calculations that seemed to work for Mercury and explained this. But we have way more evidence than that. For example, today, some of the evidence for general relativity, gravitational lensing. Remember, we say gravity is causing space-time to be curved. Well, if space-time is curved, then light moving through that space-time is going to have its path bent. In fact, the first clear test of general relativity was done during the 1919 eclipse, just a few years after Einstein published a theory, because it predicted that the light from stars would be bent as they passed close to the sun during the eclipse. That was measured and confirmed. That, incidentally, is when Einstein became famous, because that was written up in the news media all over the world. And before that, no one had heard of him. Today, we take photos like this one with the Hubble Space Telescope, where you see these strange arcs in the picture. What are those? Those are actually images of a galaxy lying behind this cluster of galaxies, and this cluster has distorted the images into these other shapes because of the way it bends the light as it goes through that curved space-time. We see this all the time, and we can even map the distribution of matter causing these strange images in this way. General relativity, I don't have time to go through the thought experiments to show you why these other things come out, but it tells you, for example, that time will run differently in gravitational fields. Again, in the movie Interstellar, that's why the time runs differently on that planet that's close to the black hole than it does up above. And this can be measured too. You might wonder, how do we measure that? We don't have any clocks on other stars, but actually we do. The way we observe other stars is by looking at their spectra, and spectra use atomic clocks in essence. And you see changes in the frequency that are emitted by different atoms. On the sun, we find the frequency of hydrogen emission, for example, is slightly different than it is here on Earth by exactly the amount predicted by relativity, because time runs slightly slower on the sun than it does on Earth due to the sun's stronger gravity. Gravitational waves are an important prediction of general relativity. We know they're real because we've seen the effects of them on orbiting close orbiting neutron star pairs. And we haven't detected them directly yet, but you should be watching the news over the next couple years because an observatory coming online called Advanced LIGO is expected or hoped for will make the first direct detections of gravitational waves sometime in the next few years. And black holes are, of course, a prediction of relativity. And now you get the idea. If gravity is curvature of space-time, stronger gravity curves it more, and a black hole is essentially when you've poked a hole in space-time. And I'd love to tell you a lot more about special and general relativity and go through how we got to all these consequences. But what I promised you at the beginning was I would tell you why this all matters. And so for the last part of the talk, I want to talk about 4 reasons why I think this is actually important for everyone to know something about. So the first reason why I think it's important for everyone to know something about relativity is the science reason, which we've talked about a little bit already. It's our modern theory of space, time, and gravity. So if you're going to do anything in science, relativity is going to be an important part of it. E equals mc squared, clear practical applications, nuclear power, and so on. In fact, there's other practical applications that are probably even closer to your heart these days. For example, your GPS navigation device is relying on satellites that are up in orbit. They're high enough up that time, even though to us you wouldn't notice the difference, but there is a small difference in the rate time runs where those satellites are because of their altitude than on the Earth because of general relativity. There's also a difference due to special relativity because of the motion of those satellites around the Earth. And the total difference between the rate at which time runs on those GPS satellites in their orbits and the rate time runs down here on Earth amounts to just nanoseconds per day. It's not anything that you would ever notice. However, those nanoseconds per day are enough that if your GPS device did not include those in the calculation, you would literally be lost. It would not get you where you wanted to go. Your GPS device is using relativity to get you where you want to go. So this is an important scientific and practical theory. The second reason why I think relativity matters and should be learned by everyone has to do with perception of reality. All of us, maybe we don't think about it on a regular basis, but all of us have some perception of what we believe the universe is kind of like. And all of us, I think, would like our perception of the universe to be based on reality. For example, you probably would not want to have a belief that Earth is the center of the universe. Why not? Because for 400 years we've known that's not reality. If you have a perception of the universe based on the idea that Earth is the center of it, that's not a very accurate perception of the universe. Well, most people today still go about their lives with this perception that space and time are independent and absolute. And guess what? For more than 100 years now, we've known that's not reality. So if you want to have a perception of the universe based on reality, you need to know something about relativity and understand the true nature of time and space. The third reason why I think everyone should know something about relativity is a little more philosophical. It's what I like to think of as what it tells us about human potential. If you really think about relativity and the ideas in it, it's really amazing. It's amazing not only because the ideas seem so strange at first, but because once you build that new common sense about them, you realize, wow, the universe actually makes more sense now than it did before. The kinds of paradoxes that Einstein encountered riding on the light beam go away. The universe makes more sense once you understand relativity. And it's kind of an amazing thing that with our minds, we were able to figure this out. Einstein, personally, the one who figured it out. And I think it's even more interesting when you think about Einstein's own life. You know, he published this theory in 1915, the year that World War I broke out and the Armenian genocide occurred. He kept working and living through horrible times. He lived through World War I, World War II. He left Germany because Hitler's rise to power. He lived through the time of the Holocaust. He was involved in the decision to build the nuclear bombs, which ultimately come from his E equals mc squared. He arguably lived through some of the worst things and had, in some cases, direct role in things that to him were mind-bogglingly awful, and yet he was an eternal optimist. He always believed that humans were capable of great things, that we would do our best. He was a believer in universal human rights long before that was fashionable for everyone. How is it that someone who saw such horrible things happen in the world that he lived in could remain such an eternal optimist? And I don't know for sure, but I have to think a big part of it is because he himself, with his own mind, had seen what human potential is by coming up with the theory of relativity. He knew personally that if we put our minds to the positive instead of the negative, there's hardly a limit to what we can do. And I think that's a lesson that would be useful for everyone to share in. The fourth and last reason I'll give you why relativity should matter to everyone is the most philosophical. It takes a little explanation. It's what I like to call your indelible mark on the universe. Now, remember I told you that space and time are measured differently by different people, but space-time has a solid, in a sense, reality that is the same for everyone. And so that might make you think about, well, what would it be like? What if you could be a four-dimensional being so that you could move through space-time, four-dimensional space-time, in the same way that we can move through the three dimensions of space? In that case, you'd be able to move between points in time as well as between points in space. Well, a lot of science fiction has kind of looked at this idea. Those of you, again, who've seen the movie Interstellar, that's kind of what Matthew McConaughey's doing in that bookcase thing at the end. Right? He's moving through different points in time as well as space. If you ever get a chance, or if you've already read Kurt Vonnegut's novel Slaughterhouse-Five, he uses the same idea with his four-dimensional beings who can move about through time the same way that we can move about through space. I highly recommend reading that book. And so to try to give you a sense of what this might mean, I want you to think for a moment. You all look like very nice people to me. But maybe when you were younger, you had a little mean streak going. Maybe back in first grade, hopefully you didn't really do this, but maybe some of you did. In first grade, one time, you just whacked the kid sitting next to you for no reason at all. The kid screams. The teacher looks, what happened up there? And you just go, hey, I have no idea, I didn't do anything. And guess what? You got away with it. But what if there's four-dimensional beings? The four-dimensional beings can move through time as well as space. And at any moment, and I'm not quite sure what a moment means to a four-dimensional being, but we'll just assume that it has some meaning. At any moment, they might be looking around and, oh, there's you whacking the kid next to you. That is a moment. It's an event in space-time. It's there. You didn't get away with it. Maybe at the time you did, but you just got caught by the four-dimensional being. It's permanent. You can never undo in space-time anything that you do. Everything you do becomes permanent in space-time. And so I'll close with the last few sentences that I use in my book in the epilogue. Your life is a series of events, and this means that when you put them all together, you are creating your own indelible mark on the universe. Perhaps if everyone understood that, we might all be a little more careful to make sure that the mark we leave is one that we are proud of. And so perhaps I'm being overly naive, but I actually believe that if everyone learned about relativity, starting in elementary school, we might all treat each other a little bit better when we understand the implications of it in terms of our indelible mark on the universe. And that's pretty much all I'm going to say about relativity for tonight. But before we go to the questions, I want to just take a moment to share with you something that has really very little to do with relativity, but I'm very excited about. And it's this program. You can read the screen there. Imagine astronauts reading stories from space to children and families around the world, an exciting new program that combines literature with science education. Andy talked briefly about the program in the introduction, but this astronaut named Alvin Drew and a former director of education at Johnson Space Center, Patricia Tribe, came up with this idea. What if we had astronauts read stories from space to kids on Earth? And they decided to get that program started. And through some odd combination of coincidence and luck that I still don't fully understand, they decided that the books they wanted to read from space would be my children's books. And Alvin Drew read one of them on an electronic copy from the Space Shuttle Discovery in 2011, and then last year they launched the physical books to the space station. And I have one brief clip to show you kind of the idea.
Hi, I'm NASA astronaut Mike Hopkins on board the International Space Station, and it's one of my favorite times. It's story time from space. Now today's story is Max Goes to the Moon, a science adventure with Max the dog.
So that's basically the idea. He reads the story. Other astronauts have read the stories. The 5 books are up there. They've been read not only in English but in some other languages as well. Not everything's posted yet. Some is. Will get posted at storytimefromspace.com. I encourage you to go there and check it out. Right now, we're just getting the videos up. Eventually, hopefully, there will be all kinds of other curriculum materials to go along with it. There's some demos to demonstrate some of the science ideas in the books that will be launched this summer, and then the videos of the demos will be there, and everything's up there free for anyone in the world to look at. We've already had hits from dozens of different countries, teachers using this in their classroom, and so on. So I encourage you all to go there, Facebook Storytime from Space for updates. And incidentally, the program is a great program, but it's a little short of funds, so if you click the donate button when you go there, the people running the program, that's not me, will be very, very happy. And that's the end of my talk. Those are the 5 books that are up in orbit. If you go across the way afterwards, there's a copy of each that you can just thumb through. We don't have them for sale here tonight. There's some of them in Spanish, too. This is the book I've been talking about. I also have a book on extraterrestrial life, math education, and science education. And those are my college textbooks, and you can get more information there at jeffreybennett.com. And thank you very much.
My question is based on ignorance, my own ignorance, but in your talk you used a reference to the word year. Now the word year is relative to people on Earth. Does science have another word comparable to year that they use in measuring time? For example, what time is it on the sun?
Very good question. So really, when we say a year, we're using the Earth year as our unit because it's just a well-defined one for us. But all measures of time are officially based on atomic standards. So a year would have an actual definition in terms of a certain number of vibrations of a particular type of cesium, I believe it is. And it's that many of them. So it doesn't matter whether you're on Earth or anywhere else, a year, as we speak of it, would still be defined to be that same thing. So it has, even though it's an Earth-centric choice to use the time the Earth takes to go around the sun as our unit, it does have an absolute standard in atomic time that we can use. So if you told an alien species, this is what we mean by a year, they'd understand it. On this side of the room.
Do you think the time will ever happen far in the future that they'll look back at us and think that how naive we were to think that we couldn't travel the speed of light?
So that's an excellent question. So 2 parts to that answer. Number one, will we have been naive to think we could not go through space faster than the speed of light? No, I don't think that's ever going to happen. I think this law is pretty darn absolute. It would be a real shock because so much has been done to test this. It's hard to see how it could ever turn out not to be correct. However, general relativity, as I kind of alluded to a little bit with that curvature of space-time, it does kind of open up loopholes where you might be able to get from here to there without traveling through the universe, right? By curving the space. That's what wormholes are, kind of a loop between 2 different points in the universe without passing through the space in between them, going into hyperspace like they do in Star Wars, warp drive like they use in Star Trek. These are all things that try to exploit potential loopholes in that rule. And I don't know whether any of those are possible, but I wouldn't be surprised if someday we find there's ways to get around this limitation, but without actually violating it. This side.
I thought that the explanation for redshift was that the speed of light was relative.
No, the speed of light is absolute, And so when you get a change in frequency, you also get a corresponding change in wavelength, so that the product, wavelength times frequency, which is speed, is always still the same speed of light. So X-rays, which are very short wavelength, high frequency, travel at exactly the same speed as radio waves, which have very long wavelengths and low frequencies.
Okay, I have a question on the famous twin paradox that if a spaceship leaves Earth, it will be, to the people on Earth, time will appear to go more slowly on the spaceship. Let's say you have two spaceships, they depart. Since there's no independent observer, the person on spaceship A would think that time had slowed down in spaceship B, and the person in spaceship B would think that time had slowed down in spaceship A. Is that correct?
That is correct. And in fact, that's one of the experiments I go through in the book.
Okay, and then
you can
what
do some great stuff with this one. So you see spaceship A moving by you. You say, hey, I'm going still. You're flying by me at close to the speed of light. Your time is running slow. How do you know their time is running slow? Well, you point your super telescope at them, and you can see them moving in slow motion. But they are doing the same thing. They say it's them staying still and you going by, so they point their super telescope at you and they go, you're in super slow motion. You go, oh, no, it can't be. And so you video this and show it compared to your camera, and then you put your video in a really fast rocket and shoot it off to them, and when the rocket gets to them, you will have shown them the proof that they were the ones who had their time running slow. So you can prove it to them that they were the ones who had the time running slow. And you will succeed in that with only one minor problem, which is that right after you do that, a rocket arrives at your spaceship that has their video, and what does it show? It shows your time running slow. And guess what? This is not a problem, because you can't get together and compare clocks unless one of you decides to fire some rocket engines to go toward the other one. And when you do that, one of you will not be floating weightlessly anymore. One of you will be stuck to the back of your ship because of the firing the rocket engines. And you can still, under relativity, say, no, I'm not firing my rocket engines, I'm stuck to the back of my ship because of gravity. This was that equivalence principle that I mentioned to you before. But still, only one of you is feeling the acceleration or the gravity. And that one of you is different from the other one because you're not in equivalent reference frames anymore. And the answer to your question about the twin paradox, you can do the same thing with that experiment that we did of going to the other star. Why can't the people in the spaceship say, I didn't go anywhere, Earth went and the star shifted relative to me and came back? Well, you're the one who has to do that instantaneous acceleration at 99% of the speed of light. You're the one who has to turn around and feels those effects when you turn around, and you're therefore the one who's going to end up with the less time.
Okay,
So,
let's say, just as a thought experiment, you could put both spaceships through a similar gravitational scenario through a long period of time, and they circle around galaxies or black holes, or they both accelerate. Anyway, they have a similar gravitational history, and they get together then, both motionless relative to each other. What will the situation be as far as
it depends on
clocks?
exactly what happens in that motion. I think the key is the twin paradox is called a paradox in the sense that it's something that at first doesn't seem to make sense, but once you think it through carefully, it does make sense. And so I can't go through all the details of different situations, but in space-time, there's only one reality, and one of those people will end up having their time having been less than the other when they get back together. And it depends on who went through accelerations, who went through what gravity. And you'll for now just have to trust me on this, that if you calculate it out, there will not be any paradox left. One will be definitively younger and the other one will not.
Okay, I'm willing to just trust you on a lot of things. But you were saying that the distance galaxies that we're measuring redshift are moving away so quickly that our perception of the frequency of their light waves is also off. Did Hubble factor that in when he was calculating their distances?
That's how he figured it out. Yes, he noticed that all the galaxies were moving away from, all the galaxies had redshifts, which implies motion away from us, and that more distant ones had greater redshifts, and that's how he figured out that the universe is expanding. And
So-
since that time, it's pinning that down more precisely, the rate of that expansion. That's like what Hubble Space Telescope has done. That's allowed us to figure out how old the universe is and so on.
So, but it sounds like it's a combination of a Doppler shift as well as a relativistic shift in the frequency of the light itself.
In this particular case, you can think of it most easily as a Doppler shift. It's not a relativistic shift in this sense, although the amount of the Doppler shift, you have to use the relativistic formula to get it, not just the standard formula that you would apply at low speeds. There's a different formula when you get to speeds closer to the speed of light that you have to use. But it's best in this case actually to just think about it as a light wave stretching because the universe is expanding, so it makes everything in empty space stretch out. This side.
Thank you for your talk. I have a brief comment and a question. Briefly, the comment was about the first grade classroom where someone slugs the other kid. And I couldn't help but think, I was hoping you were going the direction that we could blame the four-dimensional being for that slug. But that's not where you were going, right?
Right. The four-dimensional being is the one who catches you in the act.
Yeah, I was kind of disappointed, but that's okay. So you just said in space-time there's only one reality. That means for all of us, I can't see something different than someone else when we're here in the same general vicinity?
In 3 dimensions, you will see something different. But if you could see in the 4 dimensions, it would be the same. And the analogy, we'll pretend this is a book here. This book in 3 dimensions, it's obviously, we all agree, this is it. But what if you take a 2-dimensional photograph of it? If you take a photograph of it when I hold it like this, it looks completely different than if you take a photograph when I hold it like this. So depending on its rotation, it in 2 dimensions may look very different, even though we all agree it's the same 3-dimensional book. And what's happening with relativity is that the 4-dimensional reality is, if we could see it, we would all agree on it. But depending on how we're moving, we're seeing essentially 3-dimensional projections of it, just like the 2-dimensional projections of this 3-dimensional book. And so different people moving relative to each other differently see more of the space, less of the time, or the other way around. That's why we measure time and space differently, even though the 4-dimensional space-time is actually the same in all cases.
So a person or a group of people witnessing a car accident could indeed see different things from their relative perspectives, actually disagree, but all be correct?
No. The car accident happened. Everyone agrees it happened.
But
what we might disagree on is exactly when and exactly how far away. But the event itself, everyone agrees that happened.
Who turned out when? Is there wiggle room there?
No.
Okay.
Sorry. Again, remember, the theory of relativity probably should have been called the theory of the 2 absolutes, and then you wouldn't be looking for all these things to be relative, right?
What caused the Big Bang?
No one knows what caused the Big Bang. In science, what we do is we look at the evidence and see where it leads us. And the evidence, expanding the universe, other things, tells us there must have been a Big Bang. We don't have anything to tell us why. So, for now at least, that is a question that science cannot address.
Is time infinite?
That also would be a question that science cannot address right now. Infinities are difficult because they go on forever. And things that go on forever are hard to make definitive statements about because you never know if you've gone far enough.
So going back to the sun shrinking and gravity still being essentially the same, if our 4th dimensional, 5th dimensional being plucked the sun out, and it would take us 8 minutes or so for the light to disappear for us, does gravity follow that same effect? Or would there be a different time?
Well, the reason in that example where the sun magically turns into a black hole, the reason I say the sun retains the same mass when it collapses into the black hole is so that the gravity doesn't change. Right. If the gravity changes, then the orbit will change and something would happen. So yes, now in that particular case, if you plucked the gravity out, you've changed the curvature of space-time there, so that information, in principle, would propagate at the speed of light outward as gravitational waves.
I have a question about...
Two more, okay.
Question about extraterrestrial life and relativity. I'm curious about your thoughts on humanity's current search for extraterrestrial life and the importance of it, and also, is the absolute speed of light going to make it difficult for us to do it anytime in the next, 500,000 years, to get information from others?
So it's an excellent question. The search for extraterrestrial life is very, very important. If you read my book, Beyond UFOs, you'll see the subtitle of that one is Its Astonishing Implications to Our Future, because I think this search is actually very, very important to the future of the human race, no matter what we find the answer to be. So I think this is a very important area of research, and I'm very glad to see the SETI Institute nearby here doing so much work in this area. As far as the implications of relativity go, the implications of relativity are that you're not going to be able to get from here to there in less time than light would get from here to there. But if you found a loophole, wormholes or stuff, then maybe you could do things differently. Or even with conventional, slower than light travel, if you're going close enough to the speed of light, you personally can make the trip in a relatively short amount of time. If you go fast enough, it's just a lot of time will pass on your home world while you're gone. And so the kind of question really comes down to is how much is that going to bother you? If you rush off to Alpha Centauri and you have a ship that's fast enough that it gets you there in a few months and back, but 8 years have passed on Earth, is that going to bother you? Well, maybe 8 years, not so much. You go to the center of the galaxy, 27,000 light years away, and come back, and you manage to have a spaceship that allows you to do it in 20 years. Great, you can do it. But 56,000 years will have passed on Earth. That might bum you out. So you have to take that into account. And the other factor is, we tend to judge these things a lot based on the fact that we don't live very long. Imagine that medicine advances and people live 10,000 years. Well, if you live 10,000 years, then a trip where you're gone for 100 might not seem like such a big deal anymore. I guess we've got one more over here.
Yeah, hi. Terrific talk. I hope I can ask this question correctly. My question is about how gravity relates to other forces that were electrostatic magnetism and stuff. And you had the quote by Newton himself saying how it seemed magic that something could operate on another object at a remote distance through a vacuum. And you had Einstein come along and explain it as, the objects are moving along the space-time curvature. And now if you look at magnets, are those also bending space-time in the same way?
No, but they don't have that, they don't suffer from that absurdity for a different reason, the way we usually think about it, which is that all of the forces, electricity and electromagnetism, the strong and weak nuclear forces, are transferred via these exchange particles that travel either at or below the speed of light. So for example, the electromagnetic force is transmitted by photons, light itself. And so we don't have that issue to worry about. But your question, maybe you didn't realize it, is actually a deeper question. How does gravity relate to these other known forces, the three other forces in nature? And the answer is we don't know. We assume that gravity needs to relate to the other three forces in nature, but we don't know how it does. We also have another problem, which is that the other three forces operate on small scales, and we can understand them through quantum mechanics. And quantum mechanics is kind of like relativity. It works really, really, really well. It's been incredibly well tested, and it explains things that are very small. Relativity explains the universe at large. And it turns out, however, that the two do not meet well. In particular, at what we call the singularity of a black hole, where general relativity tells you space becomes infinitely curved, and quantum mechanics tells you it starts fluctuating madly. Those are not the same. And so they can't both be correct about what happens there. So we have these known problems in physics today. Quantum mechanics and relativity don't meet up quite right. Gravity doesn't meet up quite right with the other three forces. And this is why I said at the beginning, we will probably someday have a different theory that goes beyond Einstein's, because we need a theory that brings all those things together. This is what Stephen Hawking calls, and the movie got its title, The Theory of Everything. It's the theory that will bring gravity together with everything else. It will unite relativity and quantum mechanics. We don't yet know what that theory is, but we assume it has to be out there, and someday we'll discover.
Great, thank you.
Thank you.
Thank you, everyone. We will now resume in the Appreciation Hall across the way, where Dr. Bennett will be signing his relativity book. So we'll see some of you